This is Hydrology, Chapter 11, Lecture 2, Flow Control Elements and Design. We've been discussing routing of flow through watersheds, but the question is, how do we control that flow to achieve our outcomes, whether it's flood management, water resource preservation, or habitat maintenance? The way we do that is through the design of flow control elements. I'm Dr. Marty Matlock. Let's get started. We'll be relying on several resources for this lecture. The USDA Natural Resource Conservation Service National Engineering Handbook, which we've explored extensively through this series of hydrology lectures. There's a draft 2011 chapter on hydraulics, and so that's what we're using for this lecture. It's available online for free. Just search for the draft 2011 version. There's an older version that's basically a scanned document in relatively low resolution that's available with much the same information. So the 2011 draft update, frankly, just provides better graphics for a process that's well understood. This is basic fluid mechanics in application. So we know that flow through a system equals area 1 times velocity 1. That's area is square units, L2, and velocity is L1 over time. In terms of unit analysis, that gives you L3 over time, or square or cubic feet over per second, or gallons per minute. But it also equals, so the area and velocity in one section equals area and velocity in another section of a pipe equals area and velocity in another section of pipe. So AN VN is Q. So that's the basic process of understanding flow through pipes. We know that flow through weirs and orifices. Orifices are basically round structures. Pipes are a form of an orifice, the opens of them especially. Follow three types of energy that are considered in hydrokinetics, the energy of water. Potential energy, which is elevation driven. Kinetic energy, which is velocity driven, and that's what drives. Those are both elements of critical flow versus subcritical flow. And then pressure. Potential energy is the ability to do work because a mass of water is higher than a given datum. So potential energy, think of it as gravitational potential energy. A mass of weight W at an elevation Z has a potential energy of Wz foot-pounds with respect to the datum. The datum, of course, is the elevation. The elevation head Z is a linear quantity of feet and a measure of energy in foot-pounds per pound. Kinetic energy is a function of the velocity of the fluid. So it's the weight of the water times the velocity in feet per second squared over gravity, 2 times gravity. So W equals 1 pound. The kinetic energy is V squared over 2G, and that's called the velocity head. Kinetic energy is what does the damage in floods. Pressure. Pressure energy is acquired by contact with other masses and is transmitted to or through the liquid mass under consideration. As such, a mass of water does not have pressure energy, but transmits it. Of course, that's how hydraulics work, is that you push water in one cylinder and it goes through a pipe or conveyance under pressure, and then it releases that pressure in another cylinder. That's how the brakes in your cars work. That's a transmission of power. Your automatic transmission uses much the same kind of process, though it uses a spinning drum to create kinetic or pressure energy. Pressure energy may be supplied by a pump or some other applied force. The pressure head, H equals P over W, also expresses energy in foot-pounds per pound. This is all energy dynamics, again, part of fluid mechanics, which you should be familiar with at this point. Now, Bernoulli's principle applies to the laws of conservation of energy to fluid flow. In frictionless flow, the sum of kinetic energy, pressure energy, and elevation energy is equal at all sections along the stream. There's no compression of the water, so there's no transmission of pressure. If we measure velocity head, pressure head, and elevation head at one station in a frictionless pipe or open channel, the total at that section would be equal to the total at a second section downstream in the same frictionless pipe or channel. Of course, there's no such thing as a frictionless pipe or channel. But once you realize that they're equal, then the only difference between them will be friction. And that's, of course, what we're seeing when we look at the energy equation cross-section in water. As we look at the pressure head, the potential energy is the Y2 over versus Y1. The kinetic energy is velocity squared over 2g upstream versus downstream. And of course, the head difference is the energy difference, which is the cumulative of both the potential energy and the kinetic energy. There is no pressure energy in an open channel that's equal upstream and downstream. Pipe flow, on the other hand, can be, when pipes are not flowing full, usually when they're up to 2/3 full, the flow in a pipe is very much like in a channel. Over 2/3 full, it becomes constrained flow. Pipe flow exists when a closed conduit of any form is flowing full. Again, for all practical purposes, over 2/3 full starts to exhibit some of the characteristics of a full pipe. In pipe flow, the cross-sectional area of flow is fixed by the cross-section of the conduit, and the water surface is not exposed to the atmosphere. The internal pressure within a pipe may be equal to or greater or less than the local atmospheric pressure. And that pressure is calculable based upon the input versus output pressures. The principles of pipe flow apply to the hydraulics of such structures as culverts, drop inlets, regular and inverted siphons, and various types of pipelines. The concept of laminar and turbulent flow are absolutely critical in pipe flow. They're necessary to understand. Laminar flow, of course, with lower Froude numbers, or Reynolds numbers, and then turbulent flow with higher Reynolds numbers. Pipe flow resistance is calculated in similar ways as channel flow using the Manning's N equation. But we have to consider now the cross-sectional flow area, the pipe flow and diameter, whether it's in inches or feet, and these are indications that are used across all of this chapter, these definitions, not just in the Reynolds equation that you see at the top, where velocity is a function of Reynolds number and hydraulic radius, and then the head loss. But we also have a number of other characteristics, the K sub C, which is head loss coefficient for conduit, K sub P, head loss coefficient for circular pipes. We have Manning's N for a number of different piping materials. Notice that we have Manning's N from 0.01 to 0.009, very low Manning's N. So smoother surface have lower Manning's N. The rougher surfaces have a higher Manning's N. Compared to overland flow, these are very low Manning's N's because these are materials designed and manufactured for the transmission of water. So head losses are calculated as a function of K sub V and L, the length, plus or times the kinetic energy. K sub C equals 29.164 times Manning's N squared over hydraulic radius to the 4/3. So this is very calculable, very simple. So you adapt this for circular pipes by expressing in inches instead of feet. So now we have K sub P, which is instead of a conduit, it's a pipe, and R becomes D over 4, the diameter of over 4, and D becomes DI. So now we have the equation Kp, the K of pipe is 5,087 times the Manning's N squared times over the diameter in inches of the pipe to the 4/3. And so you multiply that times the length. Keep your units correct, because we're at inches here. We got to keep our units correct. V squared over 2G. For continuity and principle, the pipe flow equation becomes Q equals A to the square root of 2GH, which is gravity times the head, over 1 plus Km, where Km is the coefficient of minor losses, plus Kp, which is pipe friction losses, times the length in feet. So now we can convert that back to feet. And I think I misspoke earlier when I talked about units here, because I think the 5087 is a inch and feet conversion to keep us in feet for length, because there we have it in length and feet as well. Just pay attention to the units. Different representations and different resources get a little tricky with the units. If you do not see the units explicitly defined in the coefficients, look it up and compare, because unit errors are common and constant throughout this work. Engineering is generally not that hard, it's just very tedious, and one of the most tedious parts is keeping your units straight. Pipe flow resistance. Here's an example of pipe flow in the cross section. This is a drop inlet spillway where we have a dam, an earthen dam, with an inlet spillway. This is called a drop inlet because you see the inlet drops the water down and then takes the water through the dam and drops it out. And so it's a 100-foot long pipe with a drop inlet, and the inlet is 20 feet below the hydraulic head, the surface of the water upstream. Notice the inverted triangle. That's the water surface here versus the inverted triangle here. Now this has an open outlet. The drop inlet, the outlet of the spillway is open. It's not submerged. If it were submerged, you just have to subtract the depths of the effective depths to get the difference in head. It's not that complicated. It does affect perhaps resistance to flow. So determine the flow of a drop inlet spillway when the water surface in the upstream pool is 20 foot higher than the outlet. The conduit barrel, that's this, is 24 inches diameter concrete pipe with a Manning's N of 0.013. So Km is equal to 1 for the bend in the entrance. That's the minor losses, because you have this entrance loss. So that's the minor losses is equal to 1. Minor losses are part of pipe flow that you learned about in hydraulics, and you can look these up in any hydraulics textbook about losses. But generally, you consider a minor loss of 1 for just a 90-degree bend. And most of the time, that's as complicated as it gets for hydrology, because we're not building complicated conduits for pipe distributions. That's a hydraulics problem, not a hydrology problem. So the solution then is Q equals A to the square root of these energy equations with the losses, because remember, if it weren't for the losses, it's just cross-sectional area velocity here, cross-sectional area velocity here. So now we're dealing with these losses and the difference in head pressure. So A equals the square root of pi over 4 d squared. So that gives us 3.14 cubic feet, because we have a 24-inch diameter pipe. So this becomes 2 squared is 4 over 4. So it's just pi feet squared. That's the area of the pipe. Kp, Km we've set as 1 because that's just the loss due to the 90-degree curve. K sub P then is the pipe losses. So we have our equation for pipe losses, and we put Manning's N in, and we have a diameter in inches to 4/3, and that gives us 0.0124. And so now Q in the outlet is calculated as 63 cubic feet per second. That's just pretty darn cool, isn't it? That we can calculate the flow of water out under this circumstance. That's the power of engineering design. You can make this thing flow the way you want it to flow by changing these parameters. Now let's take an 8-inch diameter in field diversion discharge below the water surface. So here we have the situation where we're discharging from one elevation to another. Now you can see these especially in rice fields and other flows, but you also see these in other water management systems where you're dropping water into a drop inlet spillway, a box of some sort, and then through a pipe and into another system, but it's submerged. And so the difference in hydraulic head between the two is 5 feet. So the 40-foot corrugated plastic pipe has a Manning's N of 0.020, flows full with 5 foot of head. This is 5 foot of head up here. So that means that the difference between the water level in the outlet and the difference in the inlet is 5 feet. Determine the discharge. The minor loss, because it's 90 degree, is 1. So Km is 1 again. So the discharge coefficient is the same, where we have exit coefficient is 1 here. So this is a little different. If we look at this, we have 1, exit coefficient of 1 here. The exit coefficient is the coefficient of what it takes to end the pipe here. Now, why that's important, it's just called 1 over here on the previous equation. We actually called it out K sub x. But the exit coefficient can be changed because you can put an orifice, you can reduce the pipe, you can put a spreader. There are all sorts of things you can do at the outlet, and that can reduce flow. So you have to understand that that could be a flow loss. Here it's 1, just like the flow, this pipe. So you have 1 plus 1 plus the pipe losses times the length of the pipe. And then you have the kinetic energy 2GH at the top. And so the area, of course, we calculate the area because we know that it's a corrugated pipe. Let's see, 8-inch pipe. Where do we see? That's the very top, 8-inch pipe. So we convert that to feet, and we calculate that the area is 0.349 cubic feet, the cross-sectional area of our pipe. We apply our Manning's N over the diameter in inches because this is in inches now, remember? If it's in inches, it's over 4/3. They did a bit of a trick on you here. Don't get tripped up because DI is diameter in 4/3. D feet is 2/3. So simple enough. It comes up with the equation. Again, follow the units. So Q equals 2.4 cubic feet per second. So now we know the flow under this circumstance. We can calculate it with fairly high confidence. A culvert design is probably what you'll spend most of your time as a hydrologist doing. There are a number of types of culverts. There are conduits passing under roads, railways, walking trails, any structures designed to move traffic, convey water from one side of the road to the other, railway, walking trail, or other structure. We have standard pipe culverts made out of corrugated metal. We have pipe culverts made out of concrete. You can have multiple culverts in the same round culverts. We have box culverts. You can have multiple boxes and box culverts. All of these, there's virtually all nature of culverts, even wooden culverts, especially in the Northeast. They're typically rectangular structure, oval, and arched, all sorts of structures. So movement of water through culverts, generally these are not flowing full. They're designed not to flow full. If they're flowing full, they're at flood stage. And if they're flowing full, then they are pipes. If they're not flowing full, then they are open structures and they don't have pressure. So we have unsubmerged, a number of formats for these flow control structures. Take a look at your book to see this a little better resolution. But you have unsubmerged inlets with a water surface. You have submerged inlets, which makes this more like a pipe where the water surface isn't full. You have submerged outlets, like we just saw in our example. You have outlet flowing full, where you have flow moving through with it, where there's a little bit of head. You have pipe full part of the way, and you have open flow pipes. So a number of different types of structures, and the energy gradient really about pressure is the big difference, whether you have pressure in the pipe as an energy variable or not, and it also affects the resistance to flow based upon Manning's N and how much of the wetted perimeter has to be considered. Culverts are designed either to control flow through or inlet or outlets. So your control point is the inlet or the outlet. Most of the time, you don't want the things to flood upstream, and so you have inlet control. You want this to drain so that it doesn't top over. So you control the flow up here, and you don't control below. Sometimes you control below because you have adequate storage above. That just depends on what your configuration, but most of the time it's inlet control. Under inlet control, the culvert is discharge is controlled at the culvert entrance by the depth of the headwater inlet, HWI, and the entrance geometry of the culvert, including the barrel shape and cross-sectional area and type of inlet edge, shape of wall, and other losses, what determine the flow rate. With inlet control, the entrance acts as an orifice so that flow in the culvert barrel does not become pressure flow. Headwater depth is the vertical distance from the culvert invert, that's the bottom of the culvert, at the entrance of the energy line of the headwater pool. That's depth plus velocity head. You see these indicated HW here, headwater depth. So it's the vertical distance from the culvert inlet at the entrance of the energy line. So here's the energy line, which is our pipe. Since flow in a culvert is controlled by the inlet, inlet design becomes critical. It becomes the place where you exert design control over the flow you desire in your system. A very common set of inlet designs are drop inlets. We saw those with the reservoir drop inlet barrel system for reservoir flow management. We do the same thing with just runoff management under streets and railways. So we have a box drop inlet where the water flows over a crest, and these all act as a weir. It's a broad crested weir all the way around, water flowing down and through. We'll talk about those in a moment. The same we can do in this particular bioswale, where we have water flowing through this vegetative system, and the vegetation captures much of the silt. You can see a flow line here where it's broken through, and then water drops over this crest into a box drop inlet. So we have multiple control systems here. Water controlled flowing into the vegetative channel, water flowing through the vegetative channel, then water flowing through this inlet. And all of those are design elements. Those are explicit. A more common system is the flanged or open, where you have a flared entry. So you have a wing wall, a bottom plate, a top plate, and a bevel or a crown as water enters the barrels. And so these systems can be under a number of configurations. You see one with a gradient drop and an outlet. So the design for this system is well within your tool set now. You can see the width, and you have width, height. You have material where you can calculate losses. You have potential depending on the depth. You have flow that until the depth at the top reaches the point where you flood down here, you have no pressure flow. But you can imagine where if the depth at the top reaches a certain level where you have flood, where this pipe is full, then now you have pressure, and that pressure is where it's full here to the bottom. That pressure head then is also driving and pushing water out. And so you have a shift in energy systems here. So you not only have gravitational potential energy and kinetic energy, you have pressure energy exerting on flow out. And so those things add up as water stacks up through the pipe. Designing these systems is not that complicated. We have nomographs. Nomographs are graphical solutions to multi-parameter problems. So we have nomographs where we can evaluate discharge of pipe flowing for a particular Manning's End, for example, or head loss for pipe culverts with inlet control. And so if you want to find out the discharge of pipe, which is the x-axis, you enter with the friction slope, you know that, and you want to know and you have a particular diameter of pipe, and it happens to be made of a material that has a Manning's End of 0.015. And so depending on the diameter, you can come up with a discharge. You can also enter this, if you know what discharge you want and you know what your friction slope is, this will tell you what kind of pipe size pipe you have to get to that discharge. So this is the value of a nomograph. It allows you to come up with a very rapid solution to an otherwise not very complex but tedious question of design. And the fact is, you can run the calculation, and the calculation says you need a 22.7 inch pipe to achieve the flow you're trying to achieve. You can't buy a 22.7 inch pipe. You're going to get a 24 inch pipe. So that's the value of nomographs too. It just puts you into the standard range. Another example of a nomograph is where you're trying to actually size or look at the type of entrance, whether you want a square edge with head wall, a groove edge with head wall, or a groove in projecting entrance type. And so to use scale 2 or 3, project horizontally to scale 1, then use straight line, incline line through D and Q scale. So all these nomographs have these sorts of instructions, or reverse as illustrated. So here's what we would do. Let's say we have a diameter of a culvert. We know we want to have a 42 inch culvert. And we have a 120 cubic feet per second flow. So we draw a line between the 42 inch culvert and the 120 cubic feet per second, and we keep that line going. And it comes up here and it says that for a square edge head wall, we're going to have a 2.5 inch head wall for over D diameter, which is 8.8 foot head wall. And so you can step that on through from here to 2, across this line. I think this line should be up more. It should align with the with where this dashed line hits, but they drop it down to the standard width or diameters, and that gives you standard diameters in terms of D in feet. So 2.2, 2.1, and 2.5 respectively for the 3 types of head entries. So that's the way nomographs work. You've used them before in thermodynamics, certainly. So use these. They're all in the examples and in the appendices, and you find them in other supporting documents for culvert design. Weir design hydraulics are related but different. A weir is a notch of rectangular form through which water flows. The structure containing the notch is called a weir. The edge over which the water flows is the crest. There are 2 basic types of weir crest, sharp-crested or broad-crested. In sharp-crested weir, the water goes over and doesn't make contact with the backside of the water. In broad-crested, the water flows over the top of the weir. And that's the difference in the 2. You're very familiar with broad-crested weirs. They're used everywhere. Most hydraulic structures have broad-crested weirs. That's really how we manage flow most of the time. The crest is horizontal and long in the direction of flow, so flow maintains contact with the crest rather than springing clear. The main level crest is an earthen auxiliary spillway of a flood control dam as an example of a broad-crested weir. That's what you see here. So broad-crested weirs are very familiar. We can design and manage these flows based upon the characteristics of the weir, and these are the characteristics. We can calculate Q. So this is all about energy, all about flow of energy. So we have the height of the water above the crest. We have Q coming across, and you see there's this sort of height minimum that occurs as the water dips through hydrologically. And then you have the height as it drops over. And then we sort of have a height average, which gives us the energy line and water flowing to the downstream section. Sharp-crested weirs used to measure channel flow. And so we have rectangular V-notch number of sharp-crested weirs. Sharp-crested weirs are much simpler energy dynamics. As you can see, you have basically a head, and then you have a depth above, and then you have some elevation Z, and so you have P1 and P2. That's the difference above and below, and then H2 is the height from the top of the weir to the water surface, and then Q over this system is directly proportional to height, and that's why they're very good for measuring flows. You can see a broad-crested or sharp-crested weirs here, and so if you have depth indicators along the side, you can calibrate these weirs, or you can put an automatic measurement device here, and the depth of the water going across right above the weir is explicitly correlated to Q through the system. So these are flow monitoring devices. Typical weir equation is that Q across the weir equals the weir coefficient, CW, which is dimensionless, times the weir length in in feet, times the weir head in feet to the 3 halves. So the typical coefficients, CWs, for broad-crested weirs are 2.6 to 3.1s. For OGs are rounded weirs. OG is, if you're a cabinet maker or woodworker, you know that OG is sort of a bull-nosed edge on a device, or rounded instead of a flat edge. And use those usually to reduce friction. You can have a weir coefficient of 3.2 to 4.1. Sharp-crested weirs are in between 3.2 to 3.3. Sharp-crested weirs, notice the coefficients are very tightly constrained because that's the whole point, is they're very predictable and they're very standardized. Water going over a sharp crest has a fairly constant friction coefficient. The velocity approach is the average velocity in the approach channel upstream of the weir. It's measured as a distance of 3 times the head of the weir upstream from the weir. Velocity head is added to the measured head to determine the discharge. So that if you have velocity coming through, this is a way to take kinetic energy as well as gravitational energy into effect. So you take the QW times equals CW times LW times HW plus the velocity head to the three halves. Variety of weirs and orifice designed to control flow. These things are just as varied as your imagination. Challenge is to understand the constraints of the design you're working with and to select the appropriate control structure to meet those constraints. The National Engineering Handbook 650 provides a number of examples for you. You should have an adequate background now to explore these on your own and understand them. The firm or organization or agency you're working with will have standards for their weir design, and so these are the things that you will develop expertise in as an engineer. Let's talk about design hydrographs now, because the whole purpose of designing these flow control structures is to create control or exert control over the hydrograph downstream to avoid the sort of disaster that we've seen with the Oroville Dam in California, for example, where the spillway just eroded out. And this is not a failure of a dam, this is a failure of a spillway. But the problem is the spillway eroding out could erode back up to the dam. And so this was a very dramatic example of a spillway failure where you can see the concrete under the spillway just broke through and eroded out, and it resulted in water just blasting down this hillside. Remember, the flow depth is the distance between the channel bottom and the water surface. This is very simple. And we understand our basics, diameters and characteristics of flow through a channel. And what we're trying to do is we're trying to exert this flow in such a way that we can control Q over time. And that's the way we do that is by understanding translation and attenuation. And that what we're doing is ultimately managing both translation of water downstream and attenuation of flow by changing the curve. The area under the curve is the same because except for storage, Q doesn't change. Q out equals Q in plus storage. That's the way it always is. Q out equals Q in plus storage. All we're doing is just spreading this out over the watershed over time. And that's the whole point of the watershed flood stage that we talked about in the previous lectures. It's all about energy, the cross section of the system. The energy is always predictable and manageable. We can calculate these things. We have the three types of energy. Without pressure, we have two types of energy. We have potential energy and kinetic energy. There's no pressure energy here. And the flow control systems are the cross sections. So we manage the cross sections so we understand the cross sections and resistance to flow. And what we do by managing these cross sections is we spread them out, we constrain them, we build them up, we put things in the middle of them. So all a weir is taking a large cross section and making a smaller cross section out of it. Remember that we want to understand our flow, the driver of flow, whether it's gravity or whether it's upstream kinetic energy, and that critical condition is what determines that, whether we're in subcritical or supercritical flows. And that shallow flows typically are supercritical, deeper flows typically become subcritical. As water flows through the landscape, it accumulates and aggregates, and that's what generates energy. So we have several types of routing of that water. Flood routing is the procedure that determines the timing and magnitude of a flood wave at a point on a stream from the known or assumed data at one or more points upstream. So we have a peak flow upstream. How long is it going to take to move downstream? If that peak flow is above certain levels, it's a flood, it's out of the riverbanks. How long does it take to move downstream? Flow routing is a mathematical procedure that predicts the changing magnitude, speed, and shape of a flood wave as a function of time at one or more points along the water course. Stream channel routing is the mathematical relation that calculates outflow from a stream channel once inflow lateral contributions and channel characteristics are known. So this is just routing stream channel. And then reservoir routing is what you do with reservoirs. It derives the outflow hydrograph from a reservoir from the inflow hydrograph into the reservoir with considerations of elevation, storage, and discharge characteristics of the reservoir and spillway. These major types of routing are key to understand and differentiate. You have to understand the difference between them. The movement of a flood wave down a stream system may be described in terms of translation and storage effects. That's what we were seeing with those three hydrographs stacked on top of each other. These represent characteristics of two general classes of natural flood waves. Translation involves maintaining the same hydrograph shape. We talked about that a number of times as the flood moves downstream. The storage attenuation effects involve the use of valley storage which is the cross-sectional area to reduce the peak flow and change the shape of the hydrograph. We can design it to be whatever shape we want. So this is translation, and this is attenuation. So if we don't want the downstream peak flow to be 1,100 cubic feet per second, because that's going to flood the city downstream, but so we want to reduce that, we can do that. We have the area under the curve for the outlet is going to be the same as the area under the curve for the inlet minus change in storage. If we don't have any storage, it's going to be the same area. For rivers, it's the same area. For reservoirs, you can actually increase storage in the reservoir over time to a point. Eventually, everything gets full. So base flow is a stream discharge derived from groundwater sources or interflow. It's sometimes considered to include flows from regulated lakes or reservoirs, depending on the situation. You got to know your situation, know what your base flow is made of. It fluctuates much less than storm runoff. Channel losses or transmissions may be important in arid or karst areas like Arkansas, where a significant amount of stream flow is absorbed by the porous stream bank and stream bed material. And I can tell you that is the case in most streams in Arkansas. We have as much as 50% channel losses in any given event. Channel losses represent a net loss from the channel system. You have to understand them in order to model downstream flows. Runoff volume may be reduced to account for channel losses. Yes. If the drainage area above a structure site has a climatic index, equation 21.1 of this book, of less than 1, then the direct runoff from a rainfall may be decreased to account for channel losses of influent streams. So here's this equation 21.1, where the climatic index is used to estimate channel losses and for estimating QRF. So the climatic index equals the average precipitation in inches times 100 over the average annual temperature in inches squared. Precipitation and temperature data are available, of course. We know where to find those. So we take average annual precipitation over average annual temperature. We can come up with a climatic index. You can also find these in the maps of these because they're fairly standardized by geography, the appendix of the handbook. Quick return flow is the rate of discharge that persists for some period beyond for which the 10-day principal spillway hydrograph is derived. So if we're designing a flow through a spillway, we have to think about this QRF, quick return flow. Principal spillway hydrograph is what you're trying to build. It's a 10-day principal spillway hydrograph. It includes base flow and other flows that become part of the flood hydrograph, such as rainfall that is infiltrated and appeared soon after the subflow, drainage from marshes and potholes, and snow melt. So quick return flow is a constant rate of discharge which extends the falling or receding limb of a hydrograph from the point where the quick return flow equals the principal spillway hydrograph discharge to the end of the hydrograph. So if we have a runoff hydrograph, so we have principal spillway hydrograph here, we have base flow, we have quick return flow at the bottom, and this is flow that's coming in. You can see that they can affect the taper of the hydrograph. So we have runoff, we have rainfall, we have base flow, and we have quick return flow. These are the 4 types of flows in the system. And you can see how the principal spillway hydrograph is affected by them. Quick return flow can actually extend this tail of the hydrograph. Stability and design hydrograph and freeboard hydrographs are designed to ensure that we have enough freeboard for water to move through without flooding. So runoff from rainfall with base flow is the standard hydrograph you're used to. And so the base flow without rainfall, it's just runoff hydrograph, so it's diminished a little bit. Again, these are inflow designs for your system, and you have to understand what's driving them. Typically, we deal with item C with runoff from rainfall with a base flow characteristic. That's the most common. But be aware that sometimes you have these sort of lagging flows coming in. And so if you have a spring-dominated system, you can get a quick return flow from a rainfall event that actually drives runoff up downstream after the event. Peak flow from curve number is adjusted for a 10-day runoff because flow storage structures, dams, have spillways designed to allow flow through the system under these controlled conditions. And that means you need to have a 10-day, a long term of runoff, because it doesn't just happen within the day of the storm. All dams have principal and auxiliary emergency spillways if they're competent. The principal spillway provides the outlet capacity and storage required to meet the design objectives of the structure. Principal spillway is sized to limit the frequency of operation of the auxiliary spillway and to set crest elevations of the auxiliary spillway so it does not flow during the passage of principal spillway storms. It's there for emergencies. The capacity of the principal spillway for flood retarding structures is determined using the 10-day hydrograph for the design storm. It's usually a 100-year event. So the principal spillway capacity for other structures are usually designed for the 1-day hydrograph. So if you're doing principal spillways for non-reservoirs, then you use a 1-day hydrograph. But for flood retarding structures, we use a 10-day hydrograph because of this compounding long-term flow event. 10-day runoff curve numbers are adjusted with this table. It's fairly straightforward. If you have a curve number of 87 on a 1-day curve number, which is what we typically calculate, the 10-day curve number is 76. So that's all you have to do is just translate them based upon this table. It's not that difficult. If a 100-year frequency, 10-day duration is less than 6 inches, the curve number for the 10-day storm is the same as the 1-day storm. Now, in most cases, the 100-year flood frequency is more than 6 inches. The 10-day curve number is used only with the 10-day rainfall. To keep that in mind. And those are all part of the NOAA Atlas 14 documentation. The NRCS Earthen Dam Design Manual, TR60, identifies design storms to be used in development of the principal spillway design hydrograph. This document's available to you in the literature, in the readings for this, and it's also online. Just do a Google search for TR60 Dam Design Manual. The values should be taken from the appropriate National Weather Service publications. As you know, if the drainage area above a proposed structure site is 10 square miles or less, you don't have to do aerial adjustments to storm volumes. If it's larger than 10 square miles, you have to recognize that you're going to get storms differentially manifesting across the watershed. So use area point ratios to adjust rainfall volumes. The ratios are based on a 1 and 10-day depth area curves, a figure 10 in the U.S. Weather Service TP49, but are modified to give a ratio of 1 at 10 square miles. So these are the sort of ratios. For Arkansas, assume that the QRF is greater than 1 because we have a karst environment. You add QRF to the hydrograph. The probable maximum potential precipitation for 6 hours is likely low by 15%. So we look at these probable maximum 6-hour, 10 square mile rainfalls. In Arkansas, northwest Arkansas, we're looking at 29 inches. That's probably low, significantly low. Probable maximum in Arkansas for 6-hour, 10 square mile flow is probably more like 33 inches, which is higher than it used to be in Houston. That's climate change. This is a 1985 graph. These things are going to have to be updated. We're collecting the data now. The key to successful design of an outflow structure is to understand the volume of water that must be stored over time and ensure the structure is not overtopped. Engineers learn from failure. Watch these videos to understand how easy failure is to achieve. We have the Johnstown flood of 1883, Edenville Dam failure due to seepage that undermines the structure, Smallwood Dam failure due to emergency spillway collapse, the Lake Delhi Dam, Delhi, it's not Delhi, and it should be, but they call it Delhi, Dam's failure, and the Oroville Dam in 2017. Take a look at these dam failures. And there are a whole lot more out there. They're profound, they're dramatic, and they're really inexcusable. They're unnecessary. You have a number of resources as engineers. This is serious work. People's lives and property depend on good design, effective and competent design. In the brief time that we have together, I can't teach you to be competent. That's why you have to practice for 4 years before you get your professional engineering license. That competency comes with practice under the direct tutelage and mentorship of an experienced engineer. Thank you for your attention. I look forward to seeing you next.